What if we pause to reflect on the everyday phenomena we encounter, yet constantly overlook, despite the hidden purpose behind their existence? Look closely at the edge of this simple tool that accompanied you throughout your school years. Before the zero mark, there's always a missing gap, a dead space your eyes pass over daily without thought. At first glance, it seems like a manufacturing defect, or perhaps just useless excess plastic. But in the language of industrial engineering, no millimeter is left to chance. This small gap was designed for a fundamental reason. If it were lost, this instrument would lose its measurement accuracy, becoming utterly useless and yielding flawed data. However, the deeper paradox emerges when you look at the steel instruments used by aerospace and precision mechanics engineers. There, this gap completely vanishes, and zero begins directly from the razor-sharp edge. So, why do factories place this paradox between us and the engineers? The secret lies in how materials interact with their physical environment. In our daily lives, tools are tossed into bags, dropped on the floor, and subjected to constant friction. With every impact, the outer edges endure mechanical stress, leading to material degradation and the distortion of their sharp geometry. If the zero mark began directly at the physical edge, any microscopic fracture or minor wear would instantly destroy the absolute reference point of measurement. To prevent this, protective engineering introduced what is known as a sacrificial zone. This gap acts as a physical shock absorber that takes the impact and degrades instead of the actual scale, ensuring the zero mark remains shielded and isolated, preserving measurement accuracy even after years of harsh utility. However, protecting the tool during utility is only half the story. The other half is buried within the backstage of high-speed mass manufacturing. On modern production lines, thousands of scales are printed onto massive plastic sheets at once. Then, mechanical guillotine blades drop to separate them at immense speeds. In the realm of mechanical motion, absolute perfection does not exist. Blades always possess a microscopic margin of error, shifting within fractions of a millimeter. This is where the gap functions as an intentional clearance zone, or geometric tolerance margin. It is the safe buffer wherein the industrial cutting knife is permitted to deviate slightly without slicing through the scale numbers or destroying the measurement lines. This gap is the clever solution that bridges the gap between maximum production speed and final product accuracy. The optical paradox does not stop at the boundaries of the gap. It extends to the very angles of the tool itself. If you examine the edge of a technical ruler, you will notice it isn't sharply vertical, but rather crafted with a downward-sloping bevel. This structural incline is a physical cure for a famous optical phenomenon known as parallax error. When a ruler is thick, a vertical distance is created between the scale line and the surface being measured. If you look at the numbers from an oblique angle rather than a perfectly perpendicular one, your line of sight shifts, causing an illusionary displacement that misreads the measurement. The beveled edge reduces that physical gap to near zero, forcing the scale to sit flush against the measured object. In this way, engineering ensures that light rays fall perpendicularly into your eye, unifying the reading angle and zeroing out the user's optical distortion. And if you want to witness the true pinnacle of mechanical ingenuity, look at the loose metal hook at the tip of a flexible tape measure. Many assume its shifting and wobbling is merely a manufacturing defect or loose rivets, but the truth is, it's an analog mechanical computer engineered with micrometric precision to zero out systematic error. This hook has a real physical thickness. When you pull the tape to take an external measurement, the hook slides outward so that the 0 point aligns with its inner surface, excluding its thickness from the calculation. However, when you push it against a wall for an internal measurement, the hook slides inward by the exact distance of its metal thickness, integrating that width, so it becomes the very first millimeter of the measurement. This free sliding motion guarantees a 100% accurate and calibrated result, whether you are pushing or pulling. the familiar things around us are not as simple as they appear. They are integrated engineering systems, subtly designed to manage error margins and shield our minds from randomness. If you're curious to decode more secrets behind these everyday phenomena, you've come to the right place. This is the ultimate channel for that.